Awesome. Aloha. Welcome to my talk on offensive malware analysis. As Nick mentioned, my name is Patrick Wardle. I currently work as the chief security researcher at Synack. I've worked at a variety of acronymed places before that. And very briefly, Synack runs managed bug bounty programs with vetted security researchers. All right, so what are we going to talk about today? We're going to be talking about analyzing an intriguing piece of Mac malware named FruitFly. But this analysis is going to be done in a rather different way. So we're going to start by looking at FruitFly, just a brief triage and overview, with the goal of getting just enough information about this malware so that we can build a custom command and control server for this. We're then going to talk about some tools and techniques about how to passively monitor this piece of malware. We're then going to focus on talking about how we were able to build a custom command and control server, and then how we actually tasked the malware to reveal its capabilities by just asking the right questions. And then finally, what happened when we put this custom command and control server on the internet. So our goal here is to comprehensively analyze FruitFly, but do it in somewhat of a more efficient way. So as I'm sure we're all aware, traditional methods of malware analysis, disassembly, debugging, reverse engineering, definitely work, but they're rather slow. Now, I didn't have access to an actual command and control server for FruitFly, but I figured if I built my own and then tasked the malware, I'd be able to observe its responses and then figure out its capability. So in other words, this process would allow me to coerce the malware to reveal its capabilities, its features, just by asking the right kind of questions. And I figured this would be a lot simpler in a way and a lot more efficient than fully reverse engineering via traditional means. Another benefit of this is once you have a custom command and control server, if you're able to hijack or take over the domains or register the URLs that the malware, the infection, is beaconing to, you now have the capability to actually take over other people's malware. Obviously, for cyber criminals or governments, this might be a very interesting capability. So I mentioned the target of our analysis is a macOS piece of malware named FruitFly. Now, before we build a custom command and control server and task the malware, we need to perform a basic triage to answer two questions. First, we need to know what address the malware connects to for the command and control server. That is, where does it beacon out? Where does it look? What address, what URL does it look for the command and control server? Then we also have to know what protocol the malware speaks. With these two pieces of information, then, we'll be able to create a custom command and control server that is compatible, that the malware will actually talk to. So FruitFly was discovered this past January by Malwarebytes. Was originally initially undetected by engines on VirusTotal. My friend Thomas Reed, who works at Malwarebytes, did a great blog briefly describing the malware, kind of an overview. Kind of got into some of its components, its capabilities, methods of persistence. In his blog, he touched on the fact that this piece of malware appeared to be a fairly standard Mac backdoor, but had some interesting capabilities. For example, it appeared to be able to turn on the webcam and interact with the mouse and the keyboard. Currently, we don't know what the infection vector is, but if we look at other pieces of Mac malware or look at trends, it's probably something like a malicious email, a Trojan app, or perhaps a fake web pop-up trying to get users to click on it. There's also been some forensics evidence which looks or has indicated that this malware may have been around for 5 or even 10 years, kind of flying under the radar and used in very specific targeted attacks. So that's interesting as well. Today we're going to be looking at variant B. Variant B was submitted to VirusTotal a few weeks after variant A. At the time, variant A was now being detected by AV signatures, but when variant B was submitted, it itself remained undetected. So it definitely has enough differences to be somewhat unique from variant A. When it was submitted to VirusTotal, it was submitted with the name FPS-odd to mimic a common Flash player component. And like variant A, the main component of this malware was an obfuscated Perl script. That's kind of interesting. As I mentioned, we're going to build a custom command and control server to task this malware to reveal its capabilities. And again, we need to understand the address that the malware is trying to connect to, or addresses, and also we need to understand its protocol. So let's now talk about briefly triaging this malicious Perl script, the main component of the malware, to figure out or to answer these questions. So the first thing we can do is we can beautify the script. This will make the formatting easier to read. Obviously, subroutines and variable names will still be obfuscated or nonsensical. But as we can see on the slide, once we format or beautify the script, there's basically three parts to it. There's some imports, which can shed some insight into what it's doing. It's importing some socket routines and some process-related submodules. Then there's some subroutines, which we'll talk about on the next slide, and then the main logic of the malware. So briefly, if we look at these subroutines, we get some insight into the protocol of the malware, right? These subroutines aren't really the core logic of the malware per se, but they're helper functions. So if we briefly look at them, we can perhaps gain some insight into how the malware communicates with a custom or a command and control server. So for example, if we look at subroutine G, I've got it highlighted in the slide, we can see it sending data to the command and control server. So now if we see a command invoking the G subroutine, we know it's going to respond or send some data back to the command and control server. We might not know what this data actually is, but we might see, OK, it's going to send 10 bytes back. And we might also then be able to see the format of the data that's being sent back. Similarly, if we look at the J subroutine, we can see that it's receiving some number of bytes from a command and control server. So if we create a custom command and control server, and then a command invokes the J subroutine, for example, J,9, we know that specific command requires an additional 9 bytes. So we might not know what the format or what those bytes should be, but we know that that command is expecting 9 bytes. So from our custom command and control server, we should send 9 additional bytes. After the subroutine, the malware decodes some strings. These turn out to be the primary and backup addresses of the command and control servers that the malware is trying to communicate with. There's a variety of ways we can decode the strings. Easiest is actually just to use the Perl debugger. I didn't want to spend a ton of time debugging this malware, but these decoding routines are right at the beginning. And again, the easiest way was just to step over that. So if you execute Perl-D and then the malicious script, this will start a Perl debugging section. I was actually not aware that you could debug Perl scripts in this manner. But it turns out the Perl debugger is a pretty full-featured debugger. And so there's some commands you can use, step over instructions, print out variables, et cetera, et cetera. So what we can do is we can step over the decoding routine and then just print out the strings that have been decoded. And we can see that they're the IP addresses and URLs of the command and control servers, albeit reversed. And then if we look on the slide, we can see later in the code, the malware randomly picks one of these addresses and then uses it to connect to. All right, so after decoding the primary and backup command and control servers, the malware does 3 other things. It processes some command line arguments, hides its process, and then unpacks some binary data. So if we look at the regex for the command line processing, we can see it's looking for either a port or an address : port of a command and control server it's looking to connect. So this is great because this means we can actually specify our own command and control server from the command line. So this obviously facilitates our analysis. We don't have to redirect DNS queries. We don't have to modify the host files. When we're trying to analyze this piece of malware, we can actually provide the address of the custom command and control server that the malware should connect to via its command line, and the malware will just use that. So that's great. In terms of process hiding, it just changes argv0 to Java. It's not a very sophisticated trick, but it will trick some tools, for example, the PS utility. So if you do a PS, even if the malware is running, instead of showing up as the malicious Perl script, you'll just see Java. Obviously, things like Activity Monitor or more advanced tools will not be tricked by this basic technique. And then finally, it decodes and drops some binary data. This turns out to be an embedded mock-O binary. We'll talk about that in a second. Finally, then, we get to the main processing loop. And here, the malware does 2 things. It connects and checks in with the command and control server, sends some information about the infected client, and then invokes the J subroutine to receive an additional byte from the command and control server. It then processes this byte in a massive if-else-if loop. So what this is doing is it's receiving a numeric command from the command and control server, then executing or processing this command and sending the response back to the server. So this is just a big loop. It continually executes, looking for commands from taskings from the command and control server. All right. So now we know the address of the command and control servers, or actually more importantly, we know we can actually specify our own via the command line. And we also understand the basic protocol of the malware, right? It's going to expect some numeric command, process, and then send some response back to us. Now, before we start actually building the custom command and control server, we need to talk about passively observing the malware. And this is essential because even if we have a compatible custom command and control server that the malware will talk to, that we can task the malware, if we can't observe what the malware is doing, we really might gain no insight into the malware. For example, if we task it to execute, say, command number 8, and it gives us back a 1 or a 0, OK, that's probably a success or failure case. But if we don't passively monitor the malware on the infected host, we have no idea actually what that tasking did. So the question then becomes, what do we want to monitor? And the answer is pretty much as possible. And this is because a given command might interact with the file system, right? It might create files, it might write files, it might read files. We want to be able to observe that. It might spawn off new processes or execute shell commands, so we want to monitor that as well. It might interact with the mouse and keyboard. And of course, it's probably going to send some interesting data back via the network. So we should monitor for all the events so that we can understand the malware's capabilities simply via tasking. So let's take a closer look at each of these. First is network monitoring. On macOS, this is actually pretty easy to do because there's a lot of good existing tools. For example, we can use TCP dump. Sure, we're all familiar with that. Here we monitor for DNS traffic. And we can see the malware when it's executed without any command line arguments. It's selected one of its primary command and control servers and is trying to resolve the address of that. Here we can see it actually, the response is 127.0.0.1, meaning that the primary command and control server is actually offline. We'll be talking about tasking a little bit more in a minute, but at the bottom we can see a Wireshark capture of the malware responding to command number 13. So our command and control server has told the malware to execute command number 13, and via the Wireshark capture, we can actually see that it's returning the install path. So again, we didn't know necessarily what command number 13 was, but via the network capture, we've now just determined that command number 13 returns the location where the malware itself is installed. Next up is file monitoring. We can use, again, another built-in utility, this time the fs usage command. This is a built-in macOS utility or tool that's on the system that allows you to monitor for file I/O events. So we can use this to capture any file I/O activity that's related to the malware as it's executing or responding to our tasking. Various commands we'll see will actually cause the malware to save or drop that embedded mock-O binary. And via the file monitor, we'll be able to observe this. So here we can see it saves it to /private/temp/client. So what we can do is then we can grab that mock-O binary. The malware has nicely decoded and decrypted it for us. And then we can analyze this. However, we'll see we don't actually have to spend a lot of time analyzing it because the tasking of the malware via the custom command and control server will actually reveal the capabilities of this mock-O binary. Next up, we have process monitoring, which is important because the malware is likely to spawn off new process or execute shell commands in order to process various commands that we may give it. On recent versions of macOS, dtrace, which was normally used to do such process monitoring, has been neutered due to system integrity protection. And as far as I know, there was not any open source free user mode alternative to do process monitoring on macOS. So I decided to write my own and make it, of course, open source. So here's some of the code from the library. You can see we're using the audit API. macOS has the ability to audit things, such as process events. So what we can do is we can open the audit pipe that's made available to us via the kernel and read audit events that come in, specifically ones related to process monitoring. Now, the information that comes back from this audit pipe is not in the best format, so we have to do some binary parsing and make it more digestible for clients. But this library, which is available on GitHub, will do this all for us. So here's some code on the slides showing just how easy it is to actually use this library. You basically link it in, create a process monitor object, and then you invoke the start method, and you give the start method a callback block that will be invoked by the library anytime a process start or exit event occurs. Now, the cool thing about this library is when such an event occurs, it doesn't just give you an alert and say the PID. It actually gives you a ton of really useful information about the process. For example, obviously the full path, but also then things like signing information. So you can say, is this process does it belong to Apple proper? Is it from the Mac App Store, or is it unsigned? You also get a list of processes that spawned it, so its ancestors. You get command line arguments. So a whole bunch of very useful information. So again, we'll talk more about tasking, but here you can see that when we execute command number 11, the process monitor library detects that the malware has executed the pwd command to get the malware's current working directory. I also wanted to have a mouse and keyboard sniffer. I found some old code that allowed you to intercept and modify mouse and keyboard events. However, I wanted just a pure sniffer that would work on macOS. So I wrote one based on the old code. Again, this is released open source free on GitHub. It's called snifmk. And you can see that it will capture or observe mouse and keyboard events via the Carbon API, specifically via event taps. Here's an example of us running the sniffer. We then type hi and move and click the mouse. And on the right side of the screen, you can see that the mouse and keyboard sniffer has detected these events and spit them out. So this is good because this means if the malware is interacting with the mouse and keyboard programmatically, we will be able to detect those events. OK, so now we have a good toolbox for monitoring the malware. Let's finally now get to talking about building the custom command and control server. Recall again, we can specify the address of the server via the command line, and also we understand the protocol. Specifically, we understand the malware is going to connect to our server, provide some information about the infected system, and then expects a single byte, a command line numeric argument, that it then processes as the command. So we start by building a custom command and control server, just a simple Python script that accepts connections on a port. We start this. We then execute the malware in a VM. We specify the address of this command and control server. And then when the malware executes, we can see that it connects to our server. We're not doing anything special at this point, but baby steps. This shows that the malware at least will start talking to us. So what does the malware actually do when it connects? I mentioned it sends some client information. What is the format of this client information? Well, we can go back to the malicious Perl script, briefly triage it, and we can see the format of this data. Specifically, we can see it sending things such as the version string of the malware, the hostname, and the username of the infected computer. So what we can do is we can extend the custom command and control server to parse and display this information when the malware connects. So now you can see that whenever an instance of an infected system or the malware that's running in the VM connects to our command and control server, we will parse this data and print it to the screen. Now, the meat of the custom command and control server was obviously tasking and handling command responses. Turns out there's about 25 commands that this malware supported, with a variety of subcommands, bringing the total to about 50. So the custom command and control server I wrote for this malware supported all of these 50 commands. Now, when I started, I didn't know what any of these commands actually did. So what I would do is for each command, I would triage it, looking for any command-specific protocol. For example, I looked, did the command I was creating or implemented in the custom command and control server, did it expect additional bytes? And what was the format of the response? Once I had this, again, even though I didn't know what the command actually did, I could then send the command to the malware and observe what it did on the box using the monitoring tools, and then collect the response when it responded back to me. So now we're going to talk about tasking, which is how, again, we were able to expose the capabilities of this malware. Now, unfortunately, due to time constraints, I can't go through all of the commands, but we'll focus on what I think are the most interesting. In the white paper that's in the conference proceedings, I articulate and describe all the commands. So if you want more details, I recommend you checking out the paper. And again, just to reiterate, when I started tasking the malware, again, I had no idea what each specific command did. I just knew it took a number, some command. So let's start with command number 2. If we look at the malicious Perl script, we can see it invokes J to expect 1 extra byte, and then invokes G to send a response back to the server. So we understand the protocol. We still don't know what this actually does. So when we then tell the malware to execute command number 2, we can see via the file monitor, it saves that embedded mock-o binary to /temp/client, and then executes it. And we can see this via the process monitor. Via the network capture, then, we can see it sends us back about a meg of data. So in the custom command and control server, we can save this data out to disk, and then run the file utility or dump it to see what the format of this data is, Turns out it's a PNG file, and when we open it, we can very easily see it's a screen capture. So now we know command number 2 is the screen capture command. And again, we found this out just via tasking. Remember, though, this command takes an additional byte. I had no idea what this was, right? I gave it a 0, and it gave me back a PNG. But we have this custom command and control server. So instead of having to reverse engineer the malware and see what this additional byte does, we can just send it a variety of values for this second byte and observe the response. And this will very easily tell us exactly what the second byte is. So the table on the slide, you can see that this second byte actually controls the format of the image. So you give it a 1, it gives you a black and white PNG. A 10 gives you a low-res JPEG. So this is kind of the power of a custom command and control server. All right. On to command number 8. Again, we first triage that command. We see it accepts 9 additional bytes. So this means we have to give it 9 additional bytes from the custom command and control server. And again, it drops and execs the embedded binary, passing in those 9 bytes. The response, it sends us back either 1 or 2 bytes. So unlike the screenshot command, this provides no insight into actually what this command does. So again, it's important that we have these monitoring capabilities. So we task this command, we send 8, and then we pass 9 extra bytes, 0, 1, 2, 3, 4, 5, 6. And we notice that the mouse sniffer registers a move to the XY coordinates. So watch very closely. We're going to see that on the screen, the mouse is going to move to coordinates 1, 2, 3, 4, 5, 6. So this is actually the command that, that an attacker can actually move the mouse. So again, we want to figure out what this second byte is. We know the last 8 bytes are the XY coordinates, but what about that second byte? Again, we can just task. We don't have to reverse the malware. We just give it a 0, a 1, a 2, all the way up to 7, 8, 9, 10, and observe what goes on. Turns out this is a subcommand that actually dictates what type of mouse activity the malware should do. So you can do a left click, a right click, a drag, all sorts of mouse commands. Again, look closely, bottom right of the screen. We can now see that we can send a click to a coordinate on the screen, and this will be a way for the attacker to interact with UI elements. For example, dismiss a security alert. Pretty nice feature. Final commands I want to talk about are 16 and 17. Turns out these are keyboard-related events. Again, we triage the command. We see it invokes the J subroutine to expect 1 additional byte from the command and control server, and then invokes the V subroutine, which we know drops and executes the embedded mock-O binary. So when we execute this, for example, we give it command number 16, the keyboard sniffer shows a key down event. And then if we execute command number 17, the mouse and keyboard sniffer registers a key up event. So obviously, this is the way, or this is a way, an ability of the malware to allow the remote attacker to interact again with the system by typing. So here we're going to instruct the malware to type HI in a text edit prompt. It's a little slow, but remote typing. It's kind of a neat feature. So what I did was I repeated this process for every command, right? Looked at the command just to understand the format of its protocol, tasked it, looked at the response, and then this gave me a really good understanding, basically a comprehensive understanding of all the capabilities of the malware, right? They say communication is key in this scenario. It's true even when we're talking about malware. So I talked about the most interesting ones, but you can see it also supports other commands like executing system commands, shell commands, process listing, file upload, file downloads. And one other really interesting command is you can actually set an alert that will trigger when the user is active. Obviously, this malware is used to perform interactive operations or supports that capability. And obviously, you don't want to be moving the mouse and the keyboard remotely if the user is actually sitting in front of the computer. So having the ability to detect if the user is active or not is a really interesting technique that we really don't see in Mac malware. All right, so now we have a fully compatible custom command and control server. Let's talk about hunting some flies. So as I mentioned, you ping the primary command and control servers. They all come back with 127.0.0.1, meaning they're offline. But recall we decrypted some backup command and control servers, and when we go and look online, turns out these addresses were all available. So I did what we would all probably do here and register those command and control servers, configure the DNS to point to my custom command and control server. I didn't really know what would happen, but immediately hundreds of infected hosts connected to my server. Kind of freaked me out a little bit, but at the same time, I was super stoked. Now, for each of these connections, remember that when the malware checks in, it sends us some really interesting information, specifically the username, computer name, and obviously we get an IP address as well. Now, because Macs usually name the host name the first and last name of the host or the person that set up the account, we can pretty readily identify victims. So for example, if my computer was infected, you would see the username is Patrick, the host name is Patrick Wardle's MacBook, and we'd have an IP address in Hawaii. So obviously then you could Google like Patrick Wardle Hawaii, and you would fairly easily identify me, where I work, where I live, et cetera, et cetera. Interestingly, for this malware, about 90% of the infected victims were all within the US or Canada, and there was some kind of hotspots or geolocations that really seemed to attract a large number of victims. For example, in Ohio, like 20 or 30% of the victims in the US fell in that area. So now the question is, who are these victims and why are they being targeted? Really, what was the goal of this malware? And generally, we can determine what a goal of the malware is by looking at its features. So, there's basically two types of malware. You have malware that's written by cyber criminals. It's most interested in money. So it's going to be displaying ads, ransoming files, generating fake ads, clicks, keylogging for banking creds, all that fun stuff. On the other side, you're going to have nation state. That kind of malware is going to have interactive shells for more hands-on operations. It's probably you might be turning on webcam to spy on people, screen captures, et cetera, et cetera. So if we look at FruitFly, it's kind of interesting because the victims that are being targeted are the ones that are normally targeted by financial crime, right? These everyday victims. Nation-state malware usually targets, defense contractors, political organizations, R&D labs, et cetera, not like some mom in Ohio. Unfortunately, though, in terms of features, this malware mostly aligned with the nation-state type stuff. It had the ability to turn on the webcam, interactive shells, screen capture, et cetera. So this pretty much leaves us with the only other option is a hacker is specifically targeting everyday individuals to spy on them for very perverse reasons. So I took all this information and handed off to law enforcement, basically the list of victims, who they were, and also, of course, the command and control servers. And they're kind of running with this. And I'm happy to say that, unfortunately, though, I can't really go into any specific details now. But in the next few months, we should be able to comprehensively and conclusively answer the questions that we always want to know when we're analyzing malware. Specifically, who did it, why, who the victims were, and all that stuff. So stay tuned, because I'm confident that we will have some full closure on this malware and some other interesting stuff as well. All right, so let's wrap this up. We have 2 minutes. Again, we showed today how to comprehensively analyze an interesting piece of malware just by asking the right questions. We built a custom command and control server, tasked the malware, and then observed the malware's response. Along the way, we built some interesting open source utilities that are available online. And end result, we have a full analysis of OSX FruitFly variant B. We were also then able to uncover a large number of the victims who were infected, and we worked with law enforcement as well. Of course, if we were more subversive or black hat, we could have obviously hijacked and taken over the victims and built our own botnet. But we're the good guys here, so that, of course, never happens. All right, so finally, people often ask me, how can you protect against these? As I mentioned, this malware appears to have been around for 5 to 10 years. Again, ongoing analysis by law enforcement seems to confirm this trend as well. I'm all about writing free security tools that can proactively detect some of this stuff via looking for generic behaviors and actions. So in my free time, I run a Mac security website named objectivec.com. All these tools are free. A lot of them are open source. I really hope this doesn't sound like a sales pitch. But what these tools do is they look for malicious behaviors and then trigger on that. Gave a talk last year at Virus Bulletin about Oversight. It's a utility that can detect when someone has turned on your mic or your webcam. This specific malware looks like the attacker would turn on the webcam when the user was not active or sitting in front of their computer. So the hacker would hope to view them when they're maybe in the shower, walking around the bedroom with not a lot of clothes. So the user would unlikely see the webcam light was on. But using a tool such as Oversight, you'd be alerted of that. All right, that is a wrap. Again, thank you so much for attending. Also, thank you so much for Virus Bulletin, Martijn, everyone else. Amazing conference. I think we have 30 seconds for a question or two, or I'll be around the rest of the conference if you want to guys chat or have any specific questions. So again, thank you for your time.